Welcome, everybody. This is the fourth lecture of the summer school on dynamically deformed solids. Today, we are happy to welcome back Bill Anderson from Los Alamos National Laboratory for his second lecture on shock compression of materials. I introduced Bill last time, so today I'll just hand it over directly to him so he can start sharing his slides, and we'll go from there.
Okay. Okay, can everybody see the slides okay?
Yep, perfect.
Okay, so as Michael pointed out, I'm talking about shock compression of materials. And as I warned you last week, there's going to be some recycling and redefinition of symbols that are used in equations. That just goes along with the territory in this business. To give you an idea of where we're going in today's lecture, I will have to apologize. Some bits of this lecture will be somewhat disjointed because even though it's a very specialized subject, shockwaves involves quite a range of topics, and it's really hard to cover even sort of the fundamental things that one might cover. When I give this lecture, when I'm teaching a class, typically the material I'm covering today would take about 4 hours worth of lecture time. So be prepared for a whirlwind tour. But we'll start out by discussing exactly what is a shock wave and the properties of shock waves. I will talk about relations to equations of state, and I'll touch on quasi-static compression, but only very briefly. There's not really much in the slides that will deal with that. I'll talk a little bit about how calculations are done involving shock waves, because that actually turns out to be a major issue in shock wave research. I'll discuss some of the types of measurements that are made, and then again, we'll cap the session with a couple of problems. I'm going to start off by noting that there are some differences from last week's lecture. Some are the same, so pressure is the same, mass density is the same. V is going to always be a specific volume, so volume per unit of mass. E is internal energy. If you were listening in on the discussion of the problems on Thursday, I pointed out that many people use E for Young's modulus. I specifically avoided that because I knew I was going to be using E for internal energy. And again, it's a specific quantity. So when I talk about internal energy, I will always be talking about it in terms of internal energy per unit of mass. T is temperature. U is now always going to be material speed, or because I'll be mainly speaking in one dimension, I will be using speed and velocity almost interchangeably. That's a fairly common thing in shockwave work, and there's a reason for that. And finally, capital U will always mean a wave speed. There are going to be more symbols as we go along, so I'll try and define them when we come across them. So let's start off with exactly what is a shock wave. Shock waves have been touched on in the other lectures, but we haven't really said what they are. So speaking ideally, a shock wave, it's a moving discontinuity in the thermodynamic state of a material. If you are riding along with the shock wave, you'll see material coming in at some velocity or some speed normal to the shock wave, and we'll talk about what happens when velocity is not normal. But normal to the shock wave with some velocity, which is equal actually to the speed of the shock wave relative to the material. And that material will be at some pressure. You will hear pressure and stress used relatively interchangeably in shock wave work, and there's a reason for that as well. It has some starting density and some starting internal energy. The material coming out of the shock wave has a different relative velocity, which we will be calling the shock wave speed minus UP, which is often called the particle velocity, or I've been using the term in material velocity quite a bit. It will have a different pressure, a different density, and a different internal energy. And last week, I talked about the development of a shock wave. Basically, if a material has normal compressibility, which means that the pressure derivative of the bulk modulus is greater than 0. And when I talk about bulk modulus, unless I state otherwise, it's going to be isentropic bulk modulus. In such a material, if you put in a compression wave that has a finite rise time or has a finite rise distance, so imagine this thing propagating this way, that wave will steepen because the higher pressure parts, last week I talked about these little stair steps in pressure, each one is running faster than the lower pressure parts, so that it eventually will steepen into, again, ideally, a discontinuity. And of course, that is a shock wave. Some of the important properties of shock waves are that the strain is uniaxial. The shock wave is supersonic relative to the unshocked material. So if you have some wave speed, longitudinal wave speed or bulk wave speed in the material that's defined by the bulk modulus, the shock wave will be running faster than that wave. So the material doesn't know what's coming until it gets hit. The shock wave is subsonic relative to the shocked material, and the shock wave is adiabatic. Now, I'm sure that the question is going to come up, so I'll go ahead and address it now. Is a shock wave really a discontinuity? And no, it's not, and there are physical reasons for that. First, all materials have some amount of viscosity that usually affects the shock wave and cause it to spread out. Second, you could think of a shock wave as a Fourier superposition with different frequencies traveling at different speeds. That will cause it to spread out some. But fundamentally, materials, when you get down to the atomic level, are not continua. You can't really have a discontinuity in a wave traveling in a real material. So there is a fundamental length scale that the shock wave cannot be smaller than and is always pretty much larger than, which is the atomic spacing in the material. So what makes a shock wave a shock wave? One is that one property I stated, the speed is greater than that of a normal longitudinal elastic or bulk wave, and I'll discuss the distinction there shortly. If this condition is met, then the wave can be thought of as a shock wave. an important property of shock waves is that the different parts of a shock front cannot communicate laterally because of this, what I'll call supersonic condition. And for that reason, we can always mathematically treat a shock wave as if it were locally planar. Now, I discussed the fact that if you now sit on the shock wave, so as far as you're concerned, the shock wave is stationary and the material is flowing in and out. The material changes. Its thermodynamic state changes. Pressure, density, internal energy, velocity all change. The relationships that relate those conditions on one side of the shock wave to the conditions on the other side of the shock wave, and Lauren Benedict a couple of weeks ago touched on this, are called the Rankine-Hugoniot equations. What are those equations? Well, they are simply statements of conservation of mass, energy, and momentum. So they are pretty fundamental in our world. You can't violate the Rankine-Hugoniot equations. Again, I point out the wave is assumed to be planar because it's supersonic. The equations we use work even if the wave is curved. Now, what happens behind a curved wave is a different matter. But as far as the material going through the wave is concerned, it will see the wave as a plane. I will be speaking again. I'll be freely switching back and forth between speed and velocity. Don't get hung up about that, because basically in shockwave work, because of this planarity condition, we can treat the equations as one-dimensional. Even if the shock wave is inclined, so the material is coming in at some angle, the equations work. There's simply a trigonometric change because it's the normal component of the velocity we'll be dealing with. So I'm going to go through the conservation equations, since they are so fundamental to this business, and give you very brief derivations of them, as well as at the end, the way that they are applied to what I will call the usual experimental case. Again, normal flow. We assume that the material velocity is negative. That means that it is flowing to the left in our diagram here. Stuff going to the right is positive. The shock wave in the reference frame of the material that hasn't been shocked yet is going in a positive direction, so it has a positive velocity. But it is a velocity, so the material flows into the wave at some velocity u0, and it flows out at some velocity u1. Conservation of mass requires that the flux, since we don't have converging or diverging flow lines, streamlines, the flux into and out of the wave have to be equal, which means that the density times the velocity is the same on both sides, and they're both equal to J, which is the flux. I haven't bothered putting arrows over these things. These are vectors, but generally you don't see them written as vectors because we're working again in one dimension. The only way to achieve this condition is if the ratio of the density of the material exiting the shockwave to the density of the material entering the shockwave is equal to the ratio of the initial velocity to the final velocity of the material relative to the shockwave. And because both of these velocities are negative, this is a positive quantity. Momentum. The momentum density of the material is equal to rho times u. So the flux is the same as the momentum density. So the momentum flux is rho u squared. Since the mass flux is constant, that means this quantity here is constant, any non-trivial solution, again, the momentum flux is going to be, the momentum flux is going to be a constant. So the only way to get that if the velocity isn't the same, which we're assuming it isn't, is that the momentum does have to change. So this requires an acceleration, an accelerating force in accordance with Newton's second law. The force is provided by a pressure difference, P1 minus P0, or you can think of it as a normal stress difference, normal to the shock wave. If the material spins an arbitrarily short time, because our shock wave is in this derivation arbitrarily thin, if it spins an arbitrarily short time, delta t, in the shock wave, then the amount of material in some area of the shock wave is that area times the amount of the mass flux times the delta t. So this is the amount of material inside the shock wave. Okay. The velocity difference has to be equal to the acceleration, so force divided by mass, right here, times the amount of time, this delta t. So think of this delta t and this, sorry, uppercase and lowercase. This, you have a force divided by a mass, that's an acceleration. An acceleration times a time gives you a velocity change. And force divided by area, that's a pressure. So a pressure differential now is going to be P0 minus P1. Again, the acceleration is actually going to be in the positive direction, so U1 will be less than U0. And again, you have the mass flux here. So the delta T's cancel out. F over A is your pressure differential, and J is what's left. Okay, we know that J equals rho naught U naught, and we also know it equals rho 1 U1. We can rearrange these to get this. Pressure plus rho 1 U1 squared, the P1 plus rho 1 U1 squared, is equal to P0 plus rho naught U0 squared. We already know rho naught, or U0 and U1, and that gave us rho naught and rho 1, or the ratio of those. So that allows us to then solve for a pressure difference. And I'll rearrange these shortly into the way that they're usually used. Finally is conservation of energy. Okay, because an ideal shock is a discontinuity, and even the shock waves that are actually have some finite thickness, because of the speed of the shock wave, typical shocks in the laboratory setting have rise times on the order of a nanosecond or so. Maybe a couple of 3 nanoseconds for really slow rises. As a result of that, there's no time, essentially, for heat transfer. Therefore, shocks are adiabatic. I mentioned that. Okay, total energy flux into the shock wave has to be the total energy, must equal that coming out. And that energy flux is going to be the mass flux, let's do it over here, coming in, times the sum of the enthalpy and the kinetic energy. And because these are specific quantities, there's no there's no mass here in the kinetic energy because it's kinetic energy per unit of mass. If we remember what enthalpy is, it's H plus PV, or it's E plus PV rather, it's E plus P over rho. Then that equation becomes this right here. Given the fact that V is 1 over rho, this should be J over, U is going to be J times V. So since J is U times rho, divide through by V, U is J times V. We can now rewrite this, or rewrite the conservation of momentum, I'm sorry, in this form. J is a constant. It's the same on both sides. So we can solve for J squared from that. It's simply equal to the pressure difference times the negative of the volume change. And we can rearrange that using the equations up here that went before to get the equation where the change in internal energy is 1/2 P naught plus P1 times V naught minus V1. If you were to look at this graphically, you'd realize that this is a triangle of height P1 minus P naught and base V naught minus V1 on top of a rectangle of height P naught and width V naught minus V1. This equation here, fundamental equation, it implies that the thermodynamic path followed by the material is a straight line in pressure volume space. Okay, now, the way we usually use these equations in the typical experimental setting is we know the shockwave speed. Generally, we know the particle velocity. Usually, we have the material at rest before the shockwave arrives. So now we have this US with the shockwave velocity or speed. We have a change in material velocity. I pointed out it's usually called the particle velocity. It's going to be equal to U1 minus U naught, keeping in mind that U1 and U naught are negative and U1 has a lower magnitude. So UP is positive. Then the conservation equations look like this. Rho 1 over rho naught is UP over US minus UP. Momentum, P1 minus P naught is rho naught times US times UP. And the internal energy, often it's still written like this, but it can also be written this way. And this is particularly convenient in experiments where usually the pressures are roughly zero, in many cases quite close to zero, because often the experiments are done with the sample in a vacuum chamber just because of practical considerations. In this case, the internal energy simply becomes 1/2 UP squared. So we take a sample and we cut it up into little pieces and do a bunch of experiments where we shock the material with each sample subjected to a higher pressure shock wave. And then we plot all those shock states on a graph. The locus of end states resulting from these compressions is called the Hugonio curve. It's a single line defined through a multidimensional space. And most importantly, it is not a thermodynamic path. Now, just because it's not a thermodynamic path doesn't mean that it can't be useful for thermodynamic calculations. And the reason is, of course, it defines a single line in pressure, volume, energy space. Notice I haven't said anything about temperature, and there's not going to be a lot said about temperature. The Hugonio curve, you can visualize it in a whole range of projections, but the most common are in pressure volume, in pressure particle velocity, and in shock velocity particle velocity space. Now, notice this is a straight line here. There's a reason for that. An empirical observation is that the Hugonio curves of many materials are linear, or at least piecewise linear, within the resolution of the data in the US UP plane. So here's an example. This is magnesium, just your garden variety pure magnesium. This is the Hugonio. This is from the Los Alamos Shock Hugonio Data Compendium, published by Marsh, or edited by Marsh. And you can see that it's straight enough that, in fact, people fit straight lines to these things. Now, here's a somewhat more complicated situation. This is praseodymium. And here, it's sort of piecewise linear. There's actually a little curvature to here. Occasionally, people will add a quadratic term to this, but the vast majority of tabulated Hugonio fits are just straight lines in US UP space. Because of this, it's very convenient to describe the Hugonio material with only these two parameters, the intercept and the slope, plus the initial density. The intercept is usually written as either C or C naught, and the slope is almost always written as S, the symbols that are used. I will be using C naught in this lecture because that's what I got used to growing up in this field, if you will. Now, if the Hugonio isn't the path, what is? It's the Rayleigh line. And remember that I noted back a few slides back that the equations indicated that the path taken by the material in pressure volume space during a shock wave is a straight line. Well, that means that the Rayleigh line is a straight line in pressure volume space. And that becomes important when we're defining things. The Rayleigh line can be defined in any projection, but it is mostly used in the pressure volume case. Now, I've been using the word pressure, and the materials may often be solids, which means that under longitudinal strain, there's always some level of deviatoric stress. So the lateral components of stress, if we're using the one direction as the direction the shock wave is traveling, there's a 2-2 component and a 3-3 component of stress that are not necessarily equal to the 1-1 component of stress, going back to last week's lecture. In a shock wave, strictly speaking, when I talk about pressure, what I'm really talking about is longitudinal stress, with the exception of the fact that these thermodynamic equations, we're talking about pressure. Except in relatively weak shock waves, it turns out the deviatoric stresses are so small relative to the pressure that we usually ignore them. And the assumption is made that the stress is actually hydrostatic. And we call this the hydrostatic approximation. Most of our discussion will assume this approximation, but not all of it, because there are times when the hydrostatic approximation is not a good approximation. The other thing that I should point out here is why this is the case. We're talking about significant uniaxial strains, and the shear stresses that would result from those uniaxial strains are significantly greater than what the material can actually withstand. And so the material yields plastically. Once it has yielded, it's on that yield surface, and any further application of shear stress will just make it continue to flow at the same shear stress that it was at when it failed. So the material in a shock wave is sitting on the yield surface. Now, there is something called the Hugonio elastic limit, and the term elastic here should be a clue that we're now talking about something that doesn't really satisfy the hydrodynamic or hydrostatic approximation. How do the elastic wave conditions relate to Rankine-Hugonio equations? Okay, if we have a material and we drive a uniaxial strain elastic wave into the material that has a significant stress but is below the yield stress of the material, so that the material doesn't yield, it's not on the yield surface, then we have a situation that's a little bit like our uniaxial strain longitudinal wave that we talked about last week. However, that because of the fact that we now have significant stresses and significant strains, we can't necessarily assume that the material's running, that the wave is running at the, what we would call the zero pressure longitudinal wave speed. So, do the Rankine-Hugoniot equations change? Well, conservation of mass remains the same. You still have mass flux in equals mass flux out, so the density ratio obeys the same formula. Conservation of momentum remains the same. However, instead of using pressure, we'll use longitudinal stress. Now I'm not going to have 1,1 because I'm going to be using these subscripts as the initial state and the final state. Conservation of energy is a little bit more complicated because there is shear strain energy that can be non-negligible. So I'm not going to give you an equation for that right now. Now, shockwaves don't always form. And if they form, they can be unstable and they can break up. I already noted that the flow behind the shockwave has to be subsonic, which means if you were to take a little piece of the material, just as it exited the shockwave, and calculate a wave speed with the bulk modulus and Poisson's ratio and all that at the particular condition that the material's at, that wave speed will actually be greater than the speed with which the material is exiting the shockwave. If it does not obey that, then the shockwave will be unstable. We can express the requirement this way. US has to be less than or equal to UP plus that local sound speed behind the shockwave. The reason that this is the case is if the shockwave has a little disturbance in it, that disturbance will propagate away. It will carry energy with it and propagate away, and that will cause the shockwave to break up. This is actually a very common occurrence, but the shockwave doesn't totally just break up. So this occurrence can result from plastic yielding, phase transitions, chemical reactions, endothermic chemical reactions in particular. So how does that work? Well, A, what do they do? What is the effect of these things? And B, why doesn't the shockwave just break up and just go away? If you have a sufficiently strong shockwave, you can get changes in the material. It can yield, or it can, as I'm discussing here, undergo a phase transition. Now, in this particular case, the transition, this is a compressional wave. The transition will drive you to a more dense phase. And if you imagine what the pressure volume Hugonio curves of the, what I'll call the low pressure phase, the untransformed material, and the high pressure phase, the transformed material, they might look like this cartoon here. They both all can go down to some initial zero pressure volume, but the high pressure phase is always going to be at a lower volume than the low pressure phase. And so imagine you have a Hugonio curve here, and above some pressure, above some, what I'll say, Hugonio state, the thermodynamically preferred phase is going to be the high pressure phase. The material would like to jump, but it can't. The reason it can't is that phase transitions and yielding and chemistry take energy. The shock wave only provides the amount of energy given by the Rankine-Hugonio equations. So it takes some time and more compression and stronger shock waves to give enough energy to completely drive the phase transition, in this case, to completion. And so there's this mixed phase region between what we'll call the low pressure part of the Hugonio and the high pressure part of the Hugonio. Here's an example. This is graphite. You can imagine what we're doing here. We're compressing the graphite, and then we go to something here. That's got a density close to 4. That's diamond. You're creating diamond with the graphite by shocking the graphite and driving it into its high pressure phase. But the Rayleigh line that might connect, this initial state here to, say, this point right here, has a problem. It wants to intersect the Hugonio at a lower pressure. It can't do that. If the Rayleigh line is allowed to fall below the Hugonio at any lower pressure than the final state of the shock wave, it will break up. It will break up into more than one wave required to get you to that state without ever falling below the Hugonio curve at any point on its way there. So to get to C, you can't take a straight line. You have to take a detour to B and then go to C. And so if you're looking at the profile of a shock wave and pressure versus position, what you'll see is there's a wave running out in front. It's actually running faster. These two waves are not running the same speed. They are in separate waves. That takes you up to this point here, and then a separate shock wave that takes you to the final state. There are some materials, in particular certain minerals, where there are several phase transformations. One of the famous ones is the mineral calcite. That's what limestone is made out of. I forget the total number of individual waves that have been observed in calcite, but it is quite a large number. So you can have a very complicated situation like this. Now, once you get up high enough where the Rayleigh line no longer has to fall down below any part of the Hugonio, then you go back to a single wave. One of the important consequences of this is that while there are questions about shockwaves are extremely fast, how can things be in equilibrium? Shockwaves are also very high entropy and very high temperature, so things move around very fast. And the shockwave will broaden out enough to where you can get an equilibrium state, or what is essentially an equilibrium state. Now, that doesn't always happen, but it is fairly common. In fact, let's talk about that. Usually, the shockwave can be thought of as in thermodynamic equilibrium in a single material. So, aluminum, iron, magnesium. The shock compression process is fast. It involves significant entropy, significant temperature. Equilibrium is achieved very rapidly. At lower shock stresses, the Hugonio state may not be in equilibrium. And so what happens in cases quite like that, the Hugonio state is in some metastable situation, and there is relaxation to equilibrium following the Hugonio. But because the Hugonio is subsonic relative to the material behind it, that change in stress will flow forward and affect the shock wave. Now, sometimes we know an equation of state, but we don't know a Hugonio, and we would like to. When we calculate the Hugonio, we almost always make the hydrostatic approximation. So only thermodynamics, we don't have to worry about strength effects or stress deviators or things like that in order to calculate what the Hugonio looks like. The basic approach that's used when we calculate the Hugonio is the fact that the thermodynamic state of a material is independent of the path by which that state's achieved, which means we can take one path to some thermodynamic state, and we can take a totally different and possibly quite convoluted path to that same state. But once we're at that state, we're at it. It doesn't care how we got there. It only cares what it is. Usually in a shockwave calculation, the internal energy change is what we're going to use. So we equate the internal energy at some pressure volume state, which I'll call pH and VH for Hugonio pressure and volume, to some initial state, T naught and V double naught. There's a reason for this double naught. So we have a 2 PVE states that we're going to relate. And since we're assuming this is in equilibrium, we're assuming there aren't any stress deviators here, we can take two different thermodynamic paths to get there, and that allows us to constrain what the internal energy is. Now, I've got this double knot here. That is because sometimes materials are not full density. Sometimes the material may not even be in the same phase as the Hugonio state. It may be in some low pressure phase, and the Hugonio is in some high pressure phase. So this V double knot is not the same as V naught in equation of state work. It does correspond to that V naught in the Rankine-Hugoniot equations. Okay, the material could be porous, different phase, start different condition from zero pressure. We'll figure all that out. The most common thermodynamic path that is used consists of compression along some reference curve to the volume that we are interested in on the Hugoniot. And then we follow that by a constant volume heating or energy increase to the pressure on the Hugoniot. And we're going to relate that to the internal energy change achieved in the shockwave by going up the Rayleigh line. If there's a phase change, or if our reference compression curve, whatever it might be, is not the same as the state described by the initial condition, we throw in an energy of transition required to get us from that initial condition to the starting state of our reference compression curve. So here's the energy on the Hugoniot along the Rayleigh line. Here's this transition energy. Quite often, if there's no phase change, usually this is zero. There might be, if you were really niggling, if there were a different density, then there's probably some surface energy due to porosity that might make this non-zero, but it's so small that it ends up being in the noise relative to the data used to define the Hugoniot. Here's our reference, our energy along the reference compression curve. Notice I haven't done something like said, okay, this is minus the integral of PdV, because our reference compression curve could be any of a number of things we choose to define, as long as we can define it and can do the calculation. And here's our isochoric heating or isochoric energy increase. Again, notice there's no temperature in here. This quantity gamma, I think that Lauren Benedict a couple of weeks ago used a lowercase gamma. You will see it used both ways. I usually use lowercase gamma, but because I sometimes teach courses that are for physicists, and they're used to the Grün-Eisen parameter being an uppercase gamma, and I have to deal with people who use lowercase gamma for a different quantity. I've switched over to using the uppercase. Just be aware that you may see this gamma either as an uppercase or a lowercase. This is the Grün-Eisen parameter, the thermodynamic Grün-Eisen parameter. Now, in non-conductors and insulators, this quantity is defined in the same way, or is practically equal in to the same quantity that Warren Benedict spoke about a couple of weeks ago, where it is related to the vibrational frequency spectrum of the material. In metals, it has an extra contribution due to the energetics of the electrons. And so I will define this with the thermodynamic definition, which is the partial derivative of pressure with respect to internal energy at constant volume times volume. So it is a dimensionless parameter. Doesn't matter what system of units you're using. A very, very common approximation that is used, usually used, is that gamma depends explicitly only on the volume. And part of the reason that this approximation is made is that if you start giving gamma other dependencies, you become very close to danger of doing things that are thermodynamically inconsistent, because you have to be very careful. So, the most common application for these calculations assumes that we're starting at room conditions, which, from the standpoint of a shock wave in a solid, that we can just call the initial pressure 0. It is negligible in the calculations. And if we combine this assumption that with the assumption that gamma depends only on V, then that energy equivalence right here can be rewritten in this way. V naught has gone away. VH over gamma H, the gamma is now taken outside of this integral here, and so the integral then turns into just delta P over gamma. And if we rearrange this to get the Hugonio pressure on one side and everything else on the other side, we get this for our Hugonio pressure. So if we have some equation of state with, say, a Mead-Gruneisen temperature or energy dependence as a function of volume and some reference compression curve, we can calculate a point on the Hugonio for any given Hugonio volume and starting phase from that equation of state, making the assumptions that the Hugonio state is in equilibrium and the situation is hydrostatic. I haven't talked about temperature, and there's a reason. Temperature isn't addressed by the fundamental equations that we use in shockwave work. Usually, we don't know what the temperature is. We can calculate it if we make certain assumptions. I mean, we have an equation of state. If we throw in a specific heat, then we can get energies that go, or temperatures that go along with these PVE states. But we do not a priori know temperature in the shock wave. Here's the calculation we would do. If we were calculating temperature with some specific heat and this, and again, if we make some assumptions like CV is constant and that gamma depends only on volume, then our isochoric heating part right here gives us this kind of temperature change And if we know the temperature of our reference curve, then we can calculate a temperature on the Hugonio. Again, a note of caution, CV and gamma depend on one another in a fairly complicated way. And changing the behavior of one cannot be done without correspondingly and consistently changing the behavior of the others. That's why when you go and read pretty much any paper about shock waves where temperature is included, you're going to find that gamma is assumed to be constant at a given volume. It only has a volume dependence, and the specific heat is very often either assumed constant or has a simple volume dependence. Now, there's something called the Shockwave equation of state. Remember that I pointed out that the Hugonio in the US UP space is often able to be represented as a straight line, which means you can use the Hugonio, say the principal Hugonio of a material, as your reference compression curve. Now, in this case, you're not integrating along that curve. It's just that the Rankine Hugonio conditions for the reference compression curve give you an energy and a pressure and a volume. So you can use a shock wave as your reference compression curve. So it's a common thing. In fact, in lots of hydrocodes, equations of state, one of the equation of state functional forms that you might choose is a Hugonio, a C naught and an S and a rho naught as your compression curve, and a gamma or some behavior of gamma. And it just relates one Hugonio or one PVE state to a PVE state on the Hugonio using the Meagher-Neisen isochoric heating. This is a partial EOS, as is the EOS required to get this right here, because it doesn't involve all the thermodynamic potentials, in particular temperature. You need a supplemental equation. But it is a very convenient thing when information on detailed phase behavior of the material is limited. Quite often, linear, quote unquote, Hugonios sort of blast through different thermodynamic phases without the USUP Hugonio changing very much. And that's one of the reasons that this is particularly convenient. Calculating off Hugonio states, given the Hugonio, usually when somebody says off Hugonio, what they really mean is off the principal Hugonio. The principal Hugonio is the Hugonio for the full density material that's at equilibrium when it's at room conditions, starting from room conditions. So if I go and I take a piece of magnesium or something and I shock it when it's at room temperature and room pressure or zero pressure, like I said, they're practically the same, and it wasn't porous or anything weird like that, the Hugonio that shock wave puts it on is the principal Hugonio. When the principal Hugonio and Renascent parameter are known, but not much else. States away from the Hugonio are calculated by taking some chosen volume, calculating the corresponding Hugonio state. First, you have to figure out your Hugonios defined in terms of US and UP. So you calculate UP by calculating it from the Hugonio for that particular volume. Then you just go through and calculate the pressure and energy from that value of UP using C naught and S and the Rankine Hugonio equations. And then you take your Grenizen equation to get you to whatever energy or pressure you want at that volume that you've chosen. Again, if you knew the temperature on the Hugonio and you knew the specific heat, you could calculate temperature as well. As I pointed out, a shortcoming of this approach for lots of materials is that it ignores phase changes and the associated energies that go into those phase changes. In particular, when we're talking about temperature. Okay, I'm going to make a slight side trip here. I discussed porous materials as if porosity is this ideal distension. For strong shock waves, you can kind of think of it that way. And in fact, in a lot of the early work on shock waves, where people were trying to figure out the volume dependence of the Grenizen parameter, they did experiments, sort of the backward case of this, in order to, with porous materials, in order to figure out what the Grenizen parameter did as a function of volume. However, when the stresses aren't all that high, the volume, the pore collapse is controlled by more than just thermodynamics. The material strength, the yield strength, the elastic behavior of the material, the bulk material itself, comes into play. And one then needs a model to describe that. The most common model that's used is called the P-alpha model, where there's this quantity alpha, which is defined as the density of the fully solid material divided by the density of the material at whatever porosity you have. In the P-alpha model, the pressure is a function of the density alpha and the internal energy. Defined this way, there's a supplemental function required. So alpha is a function of pressure and something called alpha min. It turns out that this is a multi-valued function in elastic plastic materials. In plastic materials, for plastic behavior, alpha has a single branch, but in elastic, before you have the material has yielded, it has an infinite number of elastic branches. I'm not going to talk about Hugonios and stuff with this. I just want you to know that this is out there. The plastic branch in this looks like this. You may see it presented in slightly different ways depending on the author. Again, PS is the value that you would have if the material weren't porous. PE is a value that the material would have if it were compacted to the minimum porosity achievable, which in the P alpha model is assumed to be non-zero. So the basic thing about the P alpha model that makes it different even at high pressures from the more idealized stuff I've been talking about earlier is that it's assumed porosity never completely goes away. That's more likely to be the true case, but if the porosity gets small enough, then this term gets small enough that the approximations I presented earlier will work. Okay, now I wanted to talk about calculations involving shockwaves, and I wanted to do this for a reason. There are a lot of papers in the literature that are wrong because of mistakes people make in doing calculations with shockwaves. And the biggest problem people have has to do with reference frames and coordinate systems. Shockwave researchers will switch back and forth between different reference frames or different coordinate systems for mathematical convenience. Now, for our purposes, we're only going to talk about Cartesian coordinates. And that makes sense since we're only talking about one-dimensional things, but you will find mistakes made even in Cartesian coordinates. One other thing to point out is that last week, when I talked about stress and strain and stress were assumed to be positive in tension. When you're stretching the material, expanding the material, that was positive stress and strain. Shockwave researchers generally take stress and strain to be positive in compression. So please don't be confused by that. First thing, reference frames and coordinate systems. In your everyday life, you know, you can take a ruler and you can measure the length of a spring. And let's say we've got one here that's 5 centimeters long. Now you take that spring, you stretch it, and oh, now it's 8 centimeters long. You measured it with the same ruler, and it changed. You're working in an Eulerian reference frame when you're doing that. That is a reference frame in which the length scale is set, it's independent of material strain. However, what if the numbers, instead of being on this ruler here, were actually attached to the coils of the spring? Well, now, when you stretch the spring, the ruler still says it's 5 centimeters long. That is a Lagrangian reference frame. In a Lagrangian reference frame, the material is always in the same position, which means the material is always at rest. It does not move in the Lagrangian reference frame. Volume, density, length don't change. They are always the same in a Lagrangian reference frame. And you're going to find out that shockwave people use Lagrangian reference frames a lot. And you might ask, well, why? Again, it's because it's mathematically convenient. Now, those of you who've taken, a college level class in classical mechanics beyond sort of the freshman physics level have probably dealt with Lagrangian dynamics. The center of mass is at rest. The approach that we're using keeps that to be the case by keeping everything at rest. Everything's in its original position, so the center of mass obviously also does not move. Now, given that, we now have to worry about different types of Eulerian reference frames based on what we're defining as at rest. The common ones that we use are the laboratory frame. That's the frame that you are sitting in when you're doing an experiment, or the laboratory anyway is considered to be at rest. Another common reference frame is the initial material rest frame. So the material before the shock wave gets there is considered to be at rest. And finally, as I introduced early on, the idea that the shock wave itself is at rest, so that the material is moving relative to the shock wave, but the shock wave itself is not moving. Now, concerning wave speeds are typically only useful when given in the rest frame of the material. However, since the Lagrangian reference frame is, by definition, a material rest frame, you may end up seeing wave speeds presented in either Lagrangian or Eulerian values. And this has actually led to some confusion because shockwave experimentalists usually will give wave speeds as Lagrangian values. People who do calculations will often use Eulerian values. And if the two talk to each other, this can lead to quite a bit of confusion and acrimony. Those two Lagrangian and Eulerian reference frames can be visualized quite well using what are known as position time diagrams, or more commonly called XT diagrams. A Lagrangian XT diagram, here's one right here. You've got, in this case, two materials. And in this case, what you had was one material here hit another material at time 0. The interface between those materials is this vertical line right here. This right here happens to be a fracture that forms, but because the material isn't moving in a Lagrangian reference frame, the only things you see is waves rattling around. In this particular, the software that produced this diagram, red indicates compression, blue or aqua or turquoise indicates distension, dilation, stretching. And so you generate shock waves. The shock wave, it's a longitudinal wave. It hits a free surface. It reflects as a tensile wave of the same stress level, just negative. And so this is what a Lagrangian XT diagram looks like. If you see things like this where interfaces, surfaces, fractures, whatever, are in the same position. That's a Lagrangian diagram. Here is exactly the same calculation, the same problem, but now presented in an Eulerian diagram. In the Eulerian diagram, this impacting material was moving. And so the rear end of this thing is moving. The front end has hit, again, this target, if you will, at time 0. It sets up a shock wave that goes in. The shock wave coming off the back hasn't gotten to the rear surface quite yet. And so the rear surface is moving at the original impact velocity, whereas this is moving at a velocity that you're going to find is the same as an impedance match velocity that we talked about last week. And when a fracture happens, you can see that there's a gap opening up where the fracture occurred, and you see that these ended up being other fractures. When the shock waves hit the free surface took off at some velocity. These diagrams are quite useful for visualizing problems in shockwave work. XT diagrams in particular are exceptionally useful for looking at wave interactions or interactions of waves with interfaces and surfaces. Eulerian diagrams, which are sometimes called YT diagrams, and more confusingly, some people call Lagrangian diagrams YT diagrams, are particularly useful for visualizing material motion. And so both of these types of diagrams are useful. Now, I just mentioned that the state produced here has to do with impedance matching, and it's the same thing. Just like with elastic waves, the interactions of shock waves with material boundaries are controlled by impedance matching, where the normal components of stress and particle velocity have to be continuous. They're the same on both sides of the interface. The difference is now the impedance, instead of involving some longitudinal wave speed, involves the shock wave speed. And this number varies depending on the strength of the shock wave. If you wanted to determine whether one material has a higher impedance or lower impedance than another material, if you go and compare the pressure particle velocity projections of the Hugonio, the higher pressure Hugonio for a given particle velocity corresponds to a higher impedance. Now, one of the things that we didn't talk about last week because it wasn't really relevant was the conditions achieved by an impact, which is what this particular set of diagrams is describing. In that situation, you don't initially have a shock wave. There is no shock wave that comes in at time 0 and hits some interface. Instead, you have a projectile that hit a material and created an interface. Well, now that you've created this interface, again, the two materials have to be at the same stress, and in the laboratory frame or the rest frame of the target, if you will, they have to be moving at the same velocity. So the simplified XT diagram, Eulerian in this case, that describes this is you've got a material coming in here. This is this surface of the material. I don't show the back. And this right here is this surface of the target. I don't show the back of the target. At some impact, you generate shock waves going both directions, and you have the interface between these two moving off at a velocity equal to the particle velocity in the target that was imparted by this shock wave. The particle velocity in terms of the Hugonio in this material is equal to this impact velocity minus the velocity of this interface. So mathematically, that condition looks like this. You have subscript I, which is impactor, subscript P, which is target. Subscript D is what we call driver. So in part of the shockwave community, an impact velocity is usually written as U sub D for the driver velocity to distinguish it from a particle velocity due to a shock wave. This is usually done in the rest frame of the unshocked target. So just as here, our target is at rest, it's not moving until impact occurs. These equations are set up in that reference frame. If we assume our linear Hugonios apply to both materials, then you can calculate what the shock state is, in particular, the particle velocity in the target by solving this quadratic equation right here for the root of this. Remember, there are two roots to most quadratic equations. Sometimes they're equal to 0 if this is if this can be made a little bit more trivial. But the branch that applies in this particular one is the branch where this is a negative sign. And here are our A, B, and C. And I can leave it to you to go and actually derive this from this. Now, you can also solve this graphically. And in the old days, when people had to use slide rules or do calculations on paper for the most part, or with very large, clunky mechanical things that sat on their desks, it was quite often that people would do the solution graphically. And the way they would do that is they would take the impactor Hugonio and reflect it. So it's now going the opposite direction in pressure particle velocity space. And then they put the origin at the impact velocity. Now, if you leave the target Hugonio in its normal projection, the point that you get where the intersection occurs is the particle velocity in the target and the pressure in both. This difference right here is the particle velocity relevant for the Hugonio calculation in the impactor. If you have equations that are more complicated than a linear Hugonio that allow you to describe P as a function of U, then you can still do the equivalent of this mathematically with those more complicated equations. At an interface, impedance matching still applies, but there is a complication. And the complication is your initial state is no longer infinitesimally different from your second state, if you will, due to the incident wave, is no longer infinitesimally different from the initial state. It is significantly different. The Hugonio that this wave puts you on is not the principal Hugonio. It's not the Hugonio that this wave puts you on. It's anchored at the initial condition produced by this wave. And so you actually have to calculate a new Hugonio. Now, for many purposes, the initial, especially in non-porous materials, the initial Hugonio, the principal Hugonio, if it started off at room pressure and temperature, the initial Hugonio is close enough that you can just go from that point on the Hugonio to the next point on that same Hugonio, but that becomes dangerous. So you have to be a little careful. And the receptor, of course, it's still the same old thing. You've got an initial condition and a final condition. And the way you might calculate this, what's called a recentered Hugonio, is to use the Meagren-Eisen form and the initial Hugonio, assuming you don't really know a lot about what phases things are putting you in, to calculate the Hugonio that starts from this condition, then here behind the initial wave, and put you on this second shock state. At an interface, you can do a calculation where your initial state is here. You've got a reflected Hugonio. Say you started off here. This was the state that your first shock wave put you on. Depending on the impedance of the receptor or the acceptor material, you may slide down an isentrope to match that lower impedance, or if it's higher, you may shock up this recentered Hugonio to a higher pressure state. This curve here is an adiabat. It is usually, as I just indicated, approximated by an isentrope. And the reason is you now have a release wave. It is spreading out. Things are happening slowly. You're still at high temperature. And the assumption is that things are happening slowly enough that atomic motions have time to basically keep you isentropic when you're going down in pressure, what's called release. Now, you can also have two waves that collide with each other, or one wave that overtakes each other, another wave. You have some state. I've described it here as two shock waves. They don't have to be shock waves, but I've described some unshocked state and two waves that are approaching each other in some reference frame. Behind each wave is an initial shock state, which is unique to that wave. There's nothing that says these two waves have to produce the same pressure. They can be different strength waves. And once these waves collide or pass through each other, there is an interaction state. Impedance matching still requires you to have continuity of particle velocity and pressure. But because these are second shock states, these are on a different Hugonio from the initial shock states, there's nothing that says the thermodynamic state here has to be the same as the thermodynamic state here. The volume and energy may be different. They still obey the equation of state of the material, but the only thing that we have constrained thermodynamically is pressure across this interface between the material that was initially shocked behind shockwave B and the material that was initially shocked by shockwave A. So P and in this reference frame, particle velocity are the same. You can imagine, given that this is a vertical line, this is a Lagrangian XT diagram. P and UP in solid, or U, I will say, not UP, but P and U are the same, but V and E don't have to be the same. Now let me talk about shockwaves experiments. A shockwave is, the way it's usually generated is by sudden deposition of energy and momentum at some localized location. Impact is one of the most common means of generating a shockwave. Impact of one object into another. It's traditionally the most common experimental technique. Radiation deposition has become an important method, in particular laser radiation deposition, resulting in rapid rise in pressure. Joule heating, heating by sudden electrical energy deposition. Lightning in a thunderstorm, and the thunder generated by that lightning, that is an example of a shock wave generated in a material, air in this case, by Joule heating. Sometimes you can also generate energy or deposit energy over a period of time, resulting in a ramp wave that steepens into a shock wave. Now, there are lots of experiments that one can talk about. The most fundamental is measuring the Hugonio, because if you don't know the Hugonio of a material, you don't know how it behaves in shock compression. So usually when we measure Hugonio, it's usually the principal Hugonio, not always. Like I said, people have measured Hugonios of porous materials in particular. The thing is to point out that any given substance has an infinite number of Hugonios corresponding to the infinite number of possible starting densities, pressures, blah, blah, blah. So generally it's the principal Hugonio that gets measured. And then some calculations are done to calculate what the other Hugonios might be. The most important shockwave experiment is one designed to measure points on the Hugonio. The traditional way to do this, you use the Rankine Hugonio conditions with appropriate measurements to get US and UP of a shockwave generated by an impactor. Usually the impactor has a known Hugonio and your target has an unknown Hugonio, and then the Rankine Hugonio equations are combined with the continuity impedance matching conditions to solve for the Hugonio state. In this situation where you don't know the Hugonio of the target, but you do of the impactor, the equations are used in this form. If you know the density of both materials, then you have three things you don't know: UD, UP, and US. And so you have to measure two of these in order to get the third out of this equation. Usually the things that are measured are US and UD. And the reason that those are measured, it's easy to measure an impact velocity. Shock velocity is usually measured by arrival of the shock wave between two different levels in the target, or the time difference between impact on one side of the target and the shock wave arriving at the other side of the target, where you take your time difference and you divide it into the known difference in position between your two measurement points to get a shock wave velocity. And using that impedance matching with this equation and those measurements, and knowing what the value of C naught, which here I've left off the naught, and S for the impactor, or you can calculate what the particle velocity is that goes along with these measured values. There's one case that was actually used early on in particular to define the Hugonios of standards before there were no materials with known Hugonios, and that's something called a symmetric impact. If your target and your impactor are the same material with the same initial density, then impedance matching is going to require that the particle velocity has to be equal to 1/2 the impact velocity. And that way, if you know US, you don't have to use these equations. You already know the Hugonio point without further calculation. Now, if you go to the Marsh Compendium, as I pointed out, you will find Hugonio data for a large number of materials. Some of those materials, you can tell that there should be multiple waves. Most materials have elastic precursors at very low velocity. If the plastic shock wave is running slower than the sound speed in the material, there will be an elastic wave in front. However, a lot of the early instrumental techniques could A, only detect a single wave arrival, and B, couldn't detect relatively weak waves. And most elastic waves are relatively weak. The analysis was done using this sort of calculation where the single wave that you measured is assumed to have started from room conditions. But if there was actually a second wave, a preceding wave that was not detected in the experimental situation, that wave actually set the initial condition to be something different from the wave that was detected. And so when you are looking at experimental data from various compendia, you should be careful, particularly with older data, in how you interpret the Hugonio data for shock waves, particularly if the shock wave speed given in the compendium is less than the longitudinal sound speed in the material. That's a good indicator that there was an elastic wave there that was not detected, and that the analysis is off by some amount. Now, because these elastic waves are generally relatively weak, they may be a few kilobars in longitudinal stress, and the shock wave may be 10 or 100 times that. Quite often, the amount that the data are in error is small enough that you can pretty much ignore it. But you still need to be aware of these little details like that. Now, I talked about Hugonio experiments. Here's a sort of a laundry list of other types of experiments. Modern techniques often use Doppler velocimetry that allows time resolution. In your experiments, you can get time-resolved velocity histories, and that allows multiple waves to be detected and also allows things like release behavior to be studied. Radiography is now sometimes being used to visualize shock waves in situ. Temperature measurement using radiometry is now being used to provide information on temperature. There is another technique that has been used very infrequently because it requires neutron, it requires accelerators. And that's something called neutron resonance pyrometry, where you dope a material with something that is going to have a resonance, and you can look and see how those resonant lines broaden due to thermal motions and calculate a temperature that way. And there are many other types of experiments. I don't have time to go into all these. I'm already well over the hour and a half that I nominally have. So let's get to the problems here. Let's imagine that some material has a measured principal Hugonio that's described by a rho naught, a C naught, and an S. And that there is a thermodynamic Renascent parameter, gamma rho is equal to gamma naught rho naught. In other words, gamma rho is a constant. How would you go about calculating? So this is talking about the off-Hugonio states. How would you go about calculating the Hugonio of that same substance, but from some different density? And assume there's no difference in the starting energy and that the starting pressure is still zero. So the temperature pressure conditions are the same as this Hugonio here. That one is almost trivial given that I've pretty much described the answer. This one is a little less trivial. Okay, I have been pointing out several times the Hugonio is not a thermodynamic path. The principal Hugonio, however, is often used to approximate a release isentrope, to estimate the internal energy recovered during release back to zero pressure. And in particular, the projection of the Hugonio that is relevant is, of course, the PV projection. Because if we're assuming that the isentrope is an isentrope, then the energy change along an isentrope is minus PDV. If you take this knowledge and you assume a linear Hugonio, derive an equation using this approximation to estimate the fraction of the internal energy gained during shock compression that remains in the material after it's been released back to zero pressure. So I'm not asking for a number because the number will depend on how strong the shock wave is and on the values of C, naught and rho naught and S. But there is an equation that you can derive in order to do this calculation. This equation gets, this approximation works only really for material that is fully dense. It can be used very crudely for material that is porous, but it's a lot more difficult to use in that situation. And so those are the two problems that I have. And now I will entertain questions.
Thank you very much, Bill. We are actually 5 minutes before the hour, and if I'm not mistaken, this WebEx meeting is set to expire in 5 minutes. So we may not be able to get to questions today. So what I suggest is, I actually have a lot of questions, a lot of interesting things. What I suggest is everybody write down your questions, write them down, and then join us on Thursday for the review session, and we'll do a question and answer session at the beginning of the review session. Okay? So we'll do it that way, and if you can't make it to the review session for some reason, then just give your question to your colleague, and we'll ask all the questions there. So I also wanted to just mention, again, before we take off, where this is all going. So right now we're at lecture number 4. Bill Anderson just finished his last lecture. The review session for that, as I said, is on Thursday. That's June 25th. Bill mentioned that there's a lot to be said about the structure of a shock in terms of the elastic wave and the plastic wave and the various things that occur behind the shock. I just wanted to draw your attention to the fact that the way that the syllabus here is structured, we're picking up on that again at our lecture on August the 3rd by DJ Lucier, also from Los Alamos. So lecture number 10 is going to be on deformation behind shock waves. Before we get to lecture number 10, you're going to have 3 lectures here that talk about some of the basic mechanisms that are going to be operating. So there's going to be a sort of phenomenological description of rate dependence in plastic deformation. Then you're going to have a lecture on mechanisms of slip, followed by a lecture on mechanisms of twinning in metals. After that, we have 2 lectures where we talk about experimental techniques for dynamic deformation, including things like the plate impact experiment that Bill mentioned. And then we're going to have a lecture on various diagnostic techniques, focused especially on optical velocimetry by Dan Dolan from Sandia. So you have a couple of different things that are going to go into some more detail, some of them touching on the things that Bill mentioned today, culminating eventually in a lecture on deformation behind shock waves. And then there's going to be 3 additional lectures that talk about follow-on topics, going beyond just sort of the deformation processes themselves. So with that, I'm going to close this lecture at this moment. Again, encourage all of you to come again on Thursday. Bring all the questions that you were not able to bring today. Usually the review sessions are only last for about half an hour, so I think that there should be plenty of time to ask all of your questions then. I will definitely be joining as well to ask my questions, which I have a few. So with that, I wanted to again thank Bill for his lecture, and hope to see you all again later this week on Thursday.